Hi, my name is Ryan Booz. I'm a solutions engineer here at pganalyze. And in this new series, Postgres in Production, we aim to tackle the topics in your Postgres production workloads that are impacting you day after day. The goal of these videos is to generally be about 10 to 15 minutes, although sometimes, like today's video, it might be a little bit longer as we lay the foundation for a multi-part topic. Generally, we will first present information in slides, and then as much as possible, we want to show you hands-on through SQL exactly what's happening under the covers in your database to demonstrate the topic. So let's go ahead and get started with our first topic. Today, we're going to discuss Bloat in Postgres. Now, this will be a multi-part series about Bloat. Today, we're going to tackle tables, what Bloat is, and how vacuum impacts the way that your tables in your database are maintained over time. We'll look at some of the configuration settings that are most impactful to running an efficient and effective Postgres database, how to actually find where Bloat is through views like pgstat user tables or extensions like pgstat tuple, and then finally we will actually get into a demo so you can see exactly how these things work and the impact that Bloat is having on your database. Let's go ahead and get started. To begin the conversation, we need to first define what bloat is. And bloat is that unused space in your table or index that is actually still taking space on disk. It's caused when we delete or update rows in Postgres, and that space has not yet been reclaimed and made available for future incoming data. Now, there are a number of ways to find and look at how much bloat you have in your tables, and we'll see some of that in just a bit. Another way to think about this is what we call page density. So your data is stored on pages on disk, and we're going to look at what a page is in just a second. But if I could store the same number of rows in fewer physical pages on disk, then it means that I have less full pages. There's not as much density. I'm not packing those pages as full as I could. And so when you have more pages than you need, and they are all less full of data than they could be, then there's also some bloat. There's an indication of bloat. And so you'll see that in a couple different ways. So again, it's that unused space that we want to reclaim, and it can be seen in a number of ways, and one of which is page density. Now, why do we really care, right? If we have the data and it's still satisfying our queries, what does it matter if we have a few extra pages? Well, one of the biggest reasons is that it increases I/O within our database. Again, if I have to go and look at more pages to satisfy the query that you've just given to Postgres, then that is more I/O work. And that often causes our queries to become slower over time, particularly as your tables grow, and maintenance often falls behind, right? Anytime we have to look at more data pages to do the work that we're being asked or Postgres is being asked, often the slower things will become. And with maintenance, there is that chance that maintenance will just begin to fall behind. If it can't complete its work at every iteration, it slowly begins to fall behind, and the rest of the database suffers because of it, and the performance of the database suffers. So we keep talking about these pages. Now, I just have a really simple indicator, kind of a graphical representation of what a page might look like in Postgres. Now, this is a very simple representation. There's some great documentation both in the Postgres documentation and some other good just journals online that have described this in some good graphical ways. Now, the page is always 8 kilobytes in Postgres. It is technically configurable, but for our purposes, we will always assume it's going to be 8 kilobytes. And you will notice that most of the time we talk about them as pages. In code, they can be referred to, maybe as another word or two. And within explain plans, we'll see them by the word buffers, but really that means buffer pages, right? Pages are actually stored in memory, and that is where we're querying the information from that is actually getting produced into a result. And so whether we say pages, we say buffers, we're always talking about these 8 kilobyte pages. Now, with each page, we always have a header at the top that's 24 bytes. Every page, whether it is a table page or an index page that's storing data, has this special header area. It's just maintained by Postgres, and we're happy that it does that work. Next, at the top of the page, after that header, is where we have the item identifiers. Now, these are very small 4-byte areas that indicate where Postgres can find the data that this item identifier points to. So when I'm looking for a row of data, and it's on this page, the item identifier for that row tells Postgres, where to go find that information. And in this case, the information, the actual data, the tuples are written from the bottom up. And so you can see that this is a really good way to try and fill a page as full as we can, or at least as full as we have configured Postgres to fill these pages as data is being inserted. And the process will just continue like that until a page is full. So I insert my first row, I get the row header, and I get the data page. And then I insert another row, I get the item identifier, and I get the item itself. Now, it could be a little bit longer, or it could be a little bit shorter. Again, the process is going to continue until the page is full of data. And again, the level of fullness is something we'll talk about in another video, and reasons we might modify how full we want Postgres to try and fill a page. But from this point forward, if you see a representation like this, it's not as high def. I don't have the item identifiers, but this is a full page. And so now, if Postgres needs to insert another row, new data comes in, it has no choice but to create a new page, and we start the process all over again. Now, this is something called heap tables. And heap tables are just the process of adding new pages on top of the heap. It's a really efficient way to add information, because we don't have to worry about keeping the data actually in a certain order within these pages. Now, there are some databases that actually care about that. You can actually have what's called a clustered index, which actually determines the order of the rows on these pages up here. And because Postgres doesn't do that, it doesn't really matter what the page order is on the physical data pages. When it needs more space, it simply adds another page and keeps writing data. It's really efficient for writes, but it can cause a lot of random I/O, and it can cause some other issues when we start to delete information. And so it makes it really easy to rationalize about how big a table is. This table, as represented, has 8 pages on it, 8 pages in it. Therefore, it is 64 kilobytes. It doesn't matter that this page here is empty, essentially, right? It's just maybe it just added and it has one really small bit of information or something. This is 64 kilobytes on disk because we have 8 pages. And the process will continue, and that's, again, becomes pretty easy to rationalize about how big a table is getting. Now, the problem becomes when these pages aren't as full, again, going back to that page density, or we do something like delete a bunch of rows, we might think that deleting those rows has freed up some space on disk. This is not a file system. These are rows in a database. And in Postgres, we keep versions of rows. And so even though I deleted in this representation 2 pages worth of row data, the pages themselves didn't go away, and they won't go away even once that space is made available and reclaimed. So we still have 88 kilobytes worth of space on disk. Now, the problem is, until we reclaim that space, as we talked about earlier, this is now considered table bloat. I have 2 pages that can't be used. It's taking up space that is not available somewhere else. And so if I insert new data, I now get a new page, and the table is now 96 kilobytes. This process can really happen, obviously, very quickly in a database, right? 96 kilobytes for a table is not very big. And so consider those tables you have that are millions or maybe even billions of rows. There are tens and hundreds of millions of pages on disk to accommodate that space. And so if we're not maintaining them, we're not freeing space up as quickly as we can when we do deletes or updates, we end up with a lot of table bloat. And we see that both through these dead tuples and these pages that's just not available yet, and even in low page density. And in this case, one way to consider this is we have approximately, really round numbers, about 82%, 80% table density, give or take, right? I have 12 pages, 3 of them essentially have no data in them. 2 of them I can't even insert data into yet, and therefore I have more pages than I actually need for the rows of data I have. And so as page density goes down, right, so we have lower page density, it means we have more and more pages than we actually need to store the data. If we could shrink that, or at least prevent it from continuing, our database would be more healthy. Now, how does Postgres free up that dead tuple space? We want that space back so we aren't adding unnecessary pages and lowering the density of our table, as it were. So that is done through the process of vacuum. Now, there are a number of things that vacuum is responsible for, but one of the primary goals that we're concerned with today is reclaiming that dead tuple space, right? It's about reducing excessive bloat by making space that should be available again. And this is so important that we don't have to do this by hand. You can vacuum a table if you need to by hand, but it's so important that we rely on the auto vacuum process. And really our main goal is configuring the database and the tables so that auto vacuum works as efficiently and effectively as possible. And auto vacuum will kick in based on this formula. And it's just a percentage-based formula, essentially. Postgres will check and keep watch of how many tuples are either inserted for one set of thresholds or how many tuples are modified within the table, deleted or updated. And when it modifies, it then says, okay, take that count, multiply it by a factor, a percentage, and then add just a fixed number of rows onto that. And the reason for this fixed number of rows is just to prevent really small tables from being vacuumed continuously, because that vacuum process is a process that has to spin up and begin. And every time a table is taking away a vacuum process that might not be necessary, a larger table that actually needs to be vacuumed is being robbed of that opportunity. And so we try and prevent really small tables from being vacuumed because it's almost never really necessary for the kinds of queries and the way that Postgres works. So let's say you have 1 million rows in your table and there's a 20% scale factor in round numbers. About 200,000 rows would have to be modified or deleted, and then auto vacuum would kick in, free up any of the space that's necessary. Now, one of the problems is, as that table increases in size, that row count is going to increase with it. 20% of 1 million is very different from 20% of 100 million or 1 billion rows. And so this is something that does have to be tuned. We'll talk about that in just a second. But now the beauty is, if this is vacuumed, whether I do it manually through a vacuum or auto vacuum comes along, as soon as that space is made available and that next insert comes in, we didn't have to create a new page, right? The size of the table has not increased. We're reusing space that was already made available by previous data that's now been reclaimed, and we can reuse that. And again, this begins to lower this begins to increase table density, but it lowers the bloat. The table is not increasing as quickly as it was, and that's a good thing. Now, that custom factor is just something that's good to know about. By default, the global factor by default is 20% for auto vacuum. So 20% of the rows plus some kind of static small value is what needs to be modified. Now, you need to know about this because you can actually modify this for update heavy tables or delete heavy tables. That is when this is really essential. Anytime we have a lot of rows that are deleted, that's when we need auto vacuum to kick in, free up that space to try and reduce bloat within your tables. Now, this is not a set it and forget it, but it is something that you can do. And once we see how to find tables that are bloating, you can start to look at what these settings are and configure them for your database. It is something you need to check periodically because as your table grows, that might need to be modified, at least in Postgres 18 and below, 17 and below. You can do it simply by altering the table, and you can set any number of the values, both vacuuming and analyzing and insert vacuum and so forth through this kind of mechanism on your table as you begin to understand. Now, I did say that in Postgres 18, there's a new configuration value that's being added, the auto vacuum max threshold. And so this actually allows you for those tables that grow really quickly, if you don't want to always have to be modifying that percentage value, you can simply say, hey, by default, modify or let auto vacuum kick in after that calculation and the set number of rows is reached. That's great. But for tables that might need to be vacuumed more frequently, I can set a max threshold, and that threshold, as soon as it's reached, regardless of whether that calculation would have normally triggered an auto vacuum, it will now kick in. This is a really helpful setting in Postgres 18 and something that you should consider taking advantage of for your large tables and especially tables that are heavily updated. Now, before I get to the demo, I do want to remind you, as I've said a few times through these slides, that this does pertain to updates as well. And that's because remembering that Postgres keeps row versions around until it is sure no running transaction needs it. So even when I update a row or update something about a table, that is a delete of the previous version. It marks it for delete, and an insert of the new data. And so in this case, when there was no free space otherwise, we deleted the data and then we had to add a page to accommodate the new version of the same rows. And so this is another way that bloat happens. Now, if we have vacuum happen effectively, the next time we do an update, it might, hopefully we'll use some of that space that's now available in those previous pages. That is why vacuum is so important to keep running and running effectively through auto vacuum. Now, there are two ways for us to find this, and I'm going to show you this in the demo in just a minute. So one is pgstat user tables, and this is really a high-level kind of real-time tracking view, and it gives you the overhead. It's low overhead, so it can be run pretty frequently without really causing locking issues. But it's a kind of good enough for estimates. It shows you number of tuples deleted and updated and inserted, dead tuples and so forth. However, the numbers aren't guaranteed to be accurate because they are being updated in real time through multiple processes, and sometimes they just don't reflect exactly what's happened until the table is vacuumed and analyzed. There are a couple values that are updated with vacuum and a couple that might be updated with analyze. So when those things have run, you can rely on those numbers for some period of time. But again, this is a great way to get a rough estimate. When I run a query with some of those columns from pgstat user tables, I can see when, how many dead tuples I have, and the last time vacuum was run. Now, if I have a really big, heavily updated table and vacuum has not run in days, then I probably have a configuration issue that I need to work on to keep that dead tuple count down and keep bloat in check. Now, the more real official way to get the values is to inspect the page specifically, page by page, to actually see how many rows on each page are dead, what kind of free space is on each page, and so forth. That is done through an extension called pgstat-tuple, which comes with Postgres. It is not installed in your database by default, however. You will need to create that extension in your database, and then you can run functions like pgstat-tuple. So we select from that function on a table, and we get exact counts of how many tuples are dead, the amount of free space per page, and then the total free space in this table. And that begins to give us an idea of that page density. If there's lots of free space and not many rows, then we maybe at some point want to try and reduce the number of pages through other mechanisms. And so what I'd like to do now is show you as quickly as I can some examples of how this works in a real database. All right, so now I'd like to show you what this looks like in a database. So this is a sample database I use. It's a point of sale database around movie rentals, something you see often in the database example space. Now, this has some more realistic features to it that are specific to Postgres, even things like geospatial data. But in this case, we have about 5 years worth of rental data totaling a couple million rows currently. Now, the rental table in this database, because it's something I use frequently, has already had some of that expanding and contracting that's happened over time. And so you'll see that if I look at the rental table, I've recently run a vacuum, and so there are no dead tuples in this table. There are about 3.3 million live tuples, and over time we've inserted and deleted and updated various rows within this table. So that makes it harder to demonstrate kind of this addition of pages and contraction or freeing of space over time. And we can see that when I look at pgstat-tuple. As I go page by page, I see this database is currently this table is about 317 megabytes, but almost 50 megs is free. So if I were to start inserting rows, because there's no dead tuples, then I wouldn't get additional pages. Hopefully, Postgres would reuse that space. We want to see something a little bit different. And so I've copied this information into another table called rental2, for lack of a better name. So in the real table, in the last month of 2022, we have almost 73,000 rental records, and the same exists within our second table. I also have another copy of it just in case that 1 month of data in case I need it. So in this rental 2 table, it's brand new and fresh. We can see that it has about 3.3 million rows of data. Vacuum has run, auto vacuum has run once because I just inserted a bunch of information into it. There's been no deletes, updates, and so forth. So it's a fresh table. And this version of the table, because there's not been any other activity on it, is only 268 megabytes. It has no free space essentially. And, the actual overall tuple percentage based on all the pages that are there is about 90%. So let's do a few of the actions that we were talking about previously, which begin to cause bloat. The first is when we delete data. So I'm going to delete that 73,000 or so rows of information from this table. Now that happened very quick. It's not a very big table. It's not a lot of information. And what that's done is simply marked 72,734 rows as dead. And we can see, because no other activity had happened on this table, that those dead tuples came from deleting rows in this table. Now, we wouldn't expect the size of this table to change, and it hasn't. And the free space also has not gone up. There's still only 0.2% free space, but now there's almost 2% of space taken up by dead tuples. So we've already introduced some bloat into this table. If we don't free those dead tuples up in some way, then the database has no choice but to grow in size. We should be able to see that pretty quickly by simply reinserting those same rows again. And so when I insert those rows, it was about, I think we'll see about 5 megabytes, 5 to 6 megabytes. And I rerun that those same queries. We'll see that from pgstat user tables, we still have 72,000 and some odd dead tuples, and we know they came from deleted, but our rows are back to 3.3 million rows. So we are back to the original row count. However, when we look at this through pgstat tuple, we get a little bit different idea of what's really going on here. Number one, our table did grow by about 5 or 6 megabytes. So when we reinserted that same information, there was no available space. We had no free space. And so it had no choice but to insert additional pages. Now, there is something unique here. You'll notice that in this example, we now have, even though I have not run a vacuum, and we just looked at pgstat user tables, and it didn't run auto vacuum yet since it did the first time. But pgstat tuple shows us as having no dead tuples anymore. Now, this is something that doesn't always consistently happen in this example. But what is happening behind the scenes is sometimes when you do things like insert data and Postgres is scanning pages to find free space, if it's not currently free, but it can identify that it will be made free the next time vacuum were to run, there have been some improvements over the years in Postgres that will actually mark that space as available to be considered next time. And so as far as pgstat tuple is concerned, that space has actually been marked as available for a future process. No guarantee it will be used, but in this case, the presumption is if I were to delete and reinsert some data or insert some new data, I now have some free space, about 2%, that could be reused. So that's one example. Now, I do want to remind you that this also happens with updates. And so the exact same thing can be seen when we do an update. So I'm going to update those same exact tables. Remember, this is a delete and an insert. I expect this table will have grown about 6 megabytes. Let's go see if that's the case. And sure enough, we're back up to 274 meg. So again, we had to delete 73,000 rows, but that space then is not available immediately to the new data that we're inserting with the update. And so we're back to a very similar perspective. Now, if I were to run update again, I'm going to expect that we're going to add another 6 or so megabytes of space because we still have 73,000 dead tuples here that haven't been reclaimed. And sure enough, if I do that update, you'll see no vacuum has run and the table has increased yet again. And this is really where we begin to see problems in bloat. Delete heavy tables can have this as well, but this becomes the thing that we're not always aware of. Now, instead, if I were to quickly vacuum this table, so I have at least 72,000, maybe more rows that are available to be vacuumed up. Now, if I do that update, I think we'll see that the table is not going to grow in size. It now had free space. It didn't reduce any pages again. Remember, whether or not those pages are reduced is a nuance within Postgres and the various operations. But at least in this case, we vacuumed that table. We made space available before the next update, and so the table didn't grow anymore. It had space available for the delete and insert operation. So hopefully that helps demonstrate the importance of keeping vacuum in check, make sure that you've tuned your tables, and everything is as efficient as it can be. Now, I just want to briefly remind you what we really discussed in this first video about bloat. And really the main point is this first one. It's really about tuning the settings within Postgres to make sure auto vacuum is kicking in as efficiently and as frequently as possible to keep your tables in check. This is most necessary as tables grow and your very large tables that are update and delete heavy. And we mentioned in Postgres 18, there is a new setting about the max threshold for auto vacuum that is worth exploring, particularly on those very active, very large tables where that percentage calculation might not always be your friend in making sure the auto vacuum kicks in. And so it gives you that one other knob to turn to make sure that those tables are maintained as efficiently as possible. Now you can also consider if bloat has gotten out of control and you have a lot of pages for not a lot of data, so you have a low page density, lots and lots of empty space on each page, you could consider something like pgrepack or pgsqueeze, and we'll talk about those in a future video. The one thing I want to mention before we finish is that you'll see this often, hopefully just about anywhere you look, is trying to avoid vacuum full within your database. Sometimes when you're new to Postgres and you suddenly have realized that the table and the table bloat has maybe gotten out of control, it's easy to want to say, I'm going to vacuum this thing, vacuum full, which will try and reclaim as much space as possible. The problem is that is an exclusive lock, and it takes the lock for as long as it takes to do the vacuum. And so on a production table, a production database with a very heavily used table, as soon as you begin vacuum full, you could really bring that database to its knees and the workload itself, because nothing can take place on that table until this is done. So you really want to avoid vacuum full, and we'll get into this more in a future version, a future episode of Postgres in production to talk more about how to reclaim some of that space. I hope this has been a helpful beginning to Postgres in production and this discussion on bloat. And in the next few episodes, we'll talk about index bloat and then ways to mitigate both of these further, and even using tools like pgrepack and pgsqueeze. Thank you so much for joining us. I hope this has been helpful, and we'll see you on another episode of Postgres in production.